everyone, Katrina here, and today we're going to talk all about implicit differentiation. Be sure to subscribe for more videos like this and watch to the end to see both examples. Okay, so previously I've discussed a lot about differentiation. We have a whole derivatives playlist that we can consult for that. But in these videos, we traditionally have some sort of format where that we have y equals to f of x. That means that like our function is isolated with respect to y. For example, over here we might have y equals to 2x to the 4 plus 7x to the 1/2. We can solve this. We might have y equals to 129x to the power of 100 minus 1 over x squared. We can all solve this the normal way. And why? It's because we have, no pun intended, y isolated from the rest of our function so that we can simply differentiate y with respect to x because y equals to f of x. So today we're going to consider a new case. So what if we cannot isolate for y? What happens then? What if y is integrated within our functions? For example, what if we have something like let's say like 2y squared plus y equals to x plus 1. What if we have yx squared equals to y squared x plus or minus y to the 4? In these cases, y is just implicit, it's within our function, and we're not able to right off the bat isolate for y. We could potentially do a bunch of factoring tricks and different maneuvers and algebraic tricks to get y isolated on one side of the equation. However, that might be too much of a hassle and take up too much time, and in some cases, it might not even work. So that's where we introduce this concept of implicit differentiation. So think about this simply. If we cannot isolate for y, let's use implicit differentiation. So I'll draw your attention here to the definition that I wrote out for us today. So implicit differentiation is this technique that's used to find the derivative dy over dx, so that's the derivative of y with respect to x, of a function when it is implicitly defined. What does it mean for it to be implicitly defined? It means that y is not explicitly expressed as a function of x. That means that we don't have y equals to f of x. So this does not exist for us. We have one of these versions over here where y is integrated within our function. So for today's tutorial, I'm going to show you some step-by-step techniques that you can use as a strategy when you're trying to differentiate implicitly. And then I'll also go through 2 examples. So be sure to watch these examples because sometimes the theory can get a bit confusing, so it's really good to stay and see it in action. And again, if you're enjoying this, please subscribe and join us for this fun math journey together. Okay, so these are some steps that I have written out for all of you. So let's look at step number 1 first. So when you're doing implicit differentiation, you need to start by differentiating both sides of the equation with respect to x, okay? Because like we saw before, we might have some terms of x and y on both sides of the equation, like we might have xy plus x squared equals to y cubed minus 7, for example. So in this case, we need to differentiate both sides of the equation. Okay, step 2. So since we're differentiating implicitly, we actually have to apply chain rule. So a really simplified way of looking at this is each time that we're differentiating by y, we have to then multiply that term by dy over dx. So say, for example, we're differentiating, let's say, y squared, and we're differentiating this with respect to x, so we want d over dx of y squared. So we're going to first use the power rule here, for example, so we bring down the 2, so we get 2y. But we can't just stop there because we're differentiating implicitly with respect to y. In this case, or y with respect to x, we'd have to do 2 times y, and then multiplied by dy over dx. So that is a product of the chain rule. So this is super important right over here. So make sure that you remember this. So again, when you're differentiating by y, you have to multiply that term by dy over dx, just like we showed here in this example. So you'd use all the normal derivative rules such as PowerRule, ProductRule, QuotientRule, but then when you're differentiating with respect to that y, absolutely critical that you multiply again by this term I'm highlighting, dy over dx. Okay, this will become more apparent when we see our example. As a third step over here, we have to then rearrange our equation and factor, because the goal is we want to solve for dy over dx. So we can use different algebraic techniques here, factoring techniques, rearranging, anything you need to do in this case. And that leads us to our step 4, because we want to ultimately isolate and solve for dy over dx. We are trying to find that derivative of y with respect to x. Okay, if you guys have any questions, please feel free to comment them in the chat below. I will answer every one of them. So yeah, please don't feel discouraged by this topic. And now let's go and dive into an example, and this will help us clear up everything. Okay, so we're going to start with a bit of an easier example. So this first example, I think this equation should be familiar to a lot of us. We have x squared plus y squared equals to 9. So this is in fact the equation of a circle with a radius equal to 3, because you'd have equation of circle is x squared plus y squared equals to r squared. So here our radius, we have a circle with a radius of 3. So that's our equation that we're doing. So this one, you can see right off the bat that y is not isolated by itself on one side of the equation. But you can see pretty easily that we can probably rearrange for y if we wanted to, and it would not be that much of a hardship. We could get y squared equals to 9 minus x squared, and then by taking the square root, we'd get that y equals to plus or minus root of 9 minus x squared. Okay, so this would be option 1, and this is without implicit differentiation. Okay, so that's not what we're working on today. If you want help with regular derivatives, check out my derivatives playlist, and it covers all of that. But for today, we are going to leave it by itself, no rearranging, and we're going to go through and do implicit differentiation. Okay, so let's just consider our circle again. So x squared plus y squared equals to 9. So now we need to think about the steps. So what was step 1? We said that step 1 was differentiate both sides of our equation, okay, with respect to x. So we have d over dx, and then our left-hand side, which is x squared plus y squared, and then now we have a right-hand side of the equation, which is d over dx of 9, okay? So following our differentiation rules over here, we can, I guess, expand the derivative, or we can use like the addition rule such that we have the derivative of the first term plus the derivative of the second term. We can do this because they're separated by an addition, and then we've got the derivative of our constant on the right side. Okay, so now we can go ahead and work on solving this. So again, our regular derivatives rules apply here. So we have a power of 2. So here we can use the power rule, which is great. It's one of my favorite rules, and I feel like a lot of people share that. So everything's the same here. We're differentiating with respect to x, so we simply just have 2x by the power rule. We don't have any terms of y here, so we don't have to do anything different, okay? And now let's think about the second term. So now we're focusing on this one over here. So here we're going to start by applying the power rule, just like we did before. So we end up with 2 times, remember y is a function of x, so we 2 times y of x. I'm just writing this here to show very explicitly what's going on. And then since we have, this is a function of y, or since we have y, which is a function of x, we have to then apply the chain rule, right? So this is what we mentioned before in our steps. And we said that we then have to multiply this by dy over dx. Remember, that was a thing I said that was very important at the beginning. But that's all. You just apply the power rule like normal. And then the only thing that's different is you just have to multiply by your term dy over dx. That's it. And now let's look at the right-hand side. Well, we have the derivative of the constant, and we know that derivatives of constants are equal to 0. If you want a little aside of y, you can think of this as 9 times x to the power of 0, because anything to the power of 0 is 1. If we use the power rule, we end up with 9 times 0, and then x to the 0 minus 1. This whole thing goes to 0 because we have the 0 over here. So this is all gone. So that's why we have the 0 here on the right-hand side of the equation. Okay, so we've done the chain rule. We've taken the derivative of both sides. And now we're on the step where we just want to rearrange and solve for dy over dx. Okay, so let's just write this in another format. So we can think of this as 2x plus 2y y prime. That's just a bit cleaner, equals to 0. But we know that we are differentiating with respect to x, so we know that already. Okay, so now that we have this, we want to isolate for which term? Well, we want to isolate for this term that I've just highlighted. So let's just go ahead and do some algebra. So we have 2y y prime, and then we're going to take this guy and subtract it from both sides of the equation. So now we have the right-hand side of the equation equals to negative 2x. As a next step, we can then divide both sides of the equation by 2. So we'll do that. What are we left with? We're left with y prime equals to negative x. And now we just want to divide both sides of our equation by y. So what are we left with? We're left with y prime equals to negative x over y. And that, my friend, is our final answer. Get a big smiley face there. You've done your first implicit differentiation, and see, it was not so hard at all. What you can do as a homework exercise or practice is go back up to the top and try this version after you've rearranged it once and see if you get the same answer using regular derivative rules without implicit differentiation. So try now taking the derivative of this and double check your answer to make sure you got the same result as below. Okay, so we're going to finish off with one more example. Be sure to stay tuned and keep watching because this one is a little bit more complex. We have to now apply other derivative rules like the product rule. So just keep watching. I promise it'll be fun. So we've got x cubed y to the power of 5 plus 3x equals to 8y cubed plus 1. Okay, so this one's not as friendly to isolate for y right off the bat, so we're not even going to try that. We're just going to go straight to implicit differentiation. So remember our step 1 here is we're going to multiply both sides of the equations. We're going to take the derivative of both sides of the equation. So we've got d over dx of x cubed y to the 5 plus 3x equals to d over dx of 8y cubed plus 1. And like we said before, since we have the addition, here, we can break up the derivative. So we have d over dx of x cubed y5 plus d over dx of 3x equals to d over dx of 8y cubed plus d over dx of 1. Okay? So, this first term, let's start tackling this one. What's going on here? Well, we have the multiplication between x and y. So what happens when we have a multiplication between two terms and we're taking the derivative? Well, that calls for product rule. Again, If you need help with product rule, be sure to check out my video on product rule. So we're going to apply that. Product rule says if we're going to call this guy f and this term y, product rule is the derivative of the first times the second plus the derivative of the second times the first. So we're going to go ahead and do that. So let's try another color here. So we have f equals to x cubed. So f prime equals to what? 3x squared by power rule. G, on the other hand, equals to y to the 5. And again, y is a function. We're trying to differentiate y with respect to x. So that means when we take the derivative, we have to use chain rule. So here, first using power rule, we get 5y to the 4, and then following our chain rule, we then multiply it by dy over dx, or in short form, you can just do y prime. Okay, so then using our product rule all together, what do we get over here? We end up with the derivative of the first, which is x cubed times g, which is, derivative of the first is 3x squared multiplied by our g over here, which is just y to the 5. And then we've got plus the derivative of the second, which is 5y to the 4, y prime, and then multiply by our first, which is x cubed. Okay, so we did all that over here just to find our first term, just to find this guy right over here. This one was just a little bit more involved, again, because we had this multiplication, so we had to use product rule, and now this was a good refresher on product rule. Okay, now let's just continue on over here. So the derivative of 3x just equals to 3. And now onto our right-hand side of the equation. Okay, so we know we have a y here, so we have to use chain rule. But first we're gonna think of the outside function. So we're gonna use power rule. So we've got 3 times 8, and then y to the 3 minus 1, following power rule. And then using the chain rule, because we've got y here, we just have to multiply this by dy over dx, or y prime, okay? And then lastly, like we mentioned, we have the derivative of a constant, which equals to 0, okay? So let's try to clean all of this up a little bit and see what we get. So hopefully we can all still see the screen here at the bottom. So we're gonna take this guy first. So we've got 3x squared y 5 plus, I'm just going to rewrite this so that we have 5 times x to the power 3, y to the 4, y prime. And then we've got plus, sorry about that, plus 3. I don't know why this is getting all jiggly. Plus 3, and then our other side of equation, so 3 times 8 equals to 24. Y to the power of 3 minus 1 equals to y squared, and then we have y prime plus 0. Okay, so this is where we're at. Now comes our step 2, which was rearranging, because ultimately we want to solve for our function so that it's with respect to y prime. So we're going to have to do some grouping, some factoring, and kind of see what we get over here. Okay. So the first thing that we're going to do is we want to put both for y primes on the same side of the equation. So we're going to take this one over here, sorry, I'll do that in orange, this one here, and move it to the other side of the equation. So that means that we're actually going to take this whole term, because that's where it belongs, it's stuck to there right now, and move it over. So as a result, we have 3x squared y 5 plus 3 equals to 24y squared y prime minus 5x cubed y to the 4 y prime. Just make sure we got that all right. Okay, great. So now that we have this guy isolated on the right hand side, let's factor it out because it exists in both the terms, okay? So our left side is the same still, so 3x squared y 5 plus 3, and now we're factoring out y prime, and then we are left off with 24y squared minus 5 x cubed y to the power of 4. Amazing. So now this is actually not too bad. All we have to do is divide this guy by on both sides of the equation. So we're left with y prime equals to 3x squared y to the 5 plus 3 all over 24y squared minus 5x cubed y to the power of 4. And again, the other notation you can use is dy over dx equals whatever we have here above. Okay, these are two interchangeable notations. This one on the top is prime notation, the one on the bottom is Leibniz notation. They both mean the same thing. This one here is just a little bit more, I guess, explicit because it's telling us in particular that we are differentiating with respect to x. So I guess it's a little bit more informative for us there. But there we go. We've done the whole thing. We've followed all the steps. And we used implicit differentiation to find the derivative, found y prime. So we can make a nicer happy face. We can be very happy about that. I really hope you enjoyed this video and that you learned a new skill. If you did enjoy it, please drop a like. I really do appreciate your support, and definitely hit that subscribe button to follow along on our math journey. And I do look forward to seeing you next time.